Okay. Yeah. What I wanted to show, or what I wanted to go through with you, is this representation of the eye and the geometry of the eye, so that people understand that when we go to a two-dimensional representation, the ones, like ships going over the curve and how the light rays enter the eye, that there's a better, how should I say, association between the two, and people understand how we go from one to the other. And I think that's, I don't know, important in as much as that I want them to look at these 2D diagrams and say, yeah, these are correct, based on modeled correctly on nature and modeled correctly on geometry. Just so that there's no, I don't know, come back afterwards to say that these diagrams are not correct representations. Yeah.
Now you're talking about going from the three-dimensional tangible to the two-dimensional visible.
Yeah, I think I am. Yeah.
We're not. Because I'm sort of wondering whether you're doing that, or whether you're going from the two-dimensional spherical to the two-dimensional planar.
No, probably more the three ball, so the three eyeball. So if you like, I want to look at the eye, and then go from the eye to the two-dimensional cross-sectional view, and show people how we get there, if you know what I mean.
Cross-sectional meaning the planar view.
Yep.
And that representation you've got there of the
that was me. Sorry, I went to the construction protocol. Sorry, yeah.
The rectangles there, the squares or rectangles, are on a plane that's out in front of the eye.
Yep. Well, maybe I'll just start from the beginning of the construction, right? Because I think that will probably help the most. So if I go to the very start of this construction, then and if I just switch off the axis, then I've basically placed one point at the origin.
Right.
And then
this is the center of our 3D world, or the
that's
center
right.
of the...
Yeah, it could be where your feet are standing on a plain ground. Yeah, for example, that would be the origin O.
Or in this case, is that the center of the eye?
No, in this case, it is the center, or the place where your feet are standing, because I'll put the eye on point number 10. So if again, so that would be where the eye is.
Yep.
If I put the axis back on, so the eye's here, and my feet are here, so to speak, and this is one unit. Whatever one unit we decide afterwards to be, it could be, for example, 5 feet. Yeah.
Yep.
So I put the origin there, a normal 3D Cartesian world, right? The eye is at 10. I've then centered a sphere around the eye, which is, of course, a very big eye. If this is where the eye is, and this is a person, then this sphere is obviously not representative of the actual size of the eye. It's not to scale. No, you would have to imagine this sphere, the size of this point, or even smaller, and then inside somebody's eye socket. But what I'm trying to show here is if you like, made the eyeball bigger so that it can be seen. Yeah.
Yeah, it's like with your other diagram where you show that the circle, in that case, rather than a sphere, on the outside is an identical representation of what's on the retina anyway.
That's right. Yep, absolutely. And if you like, I want the people to realize that this is, yes, a representation of the eyeball, and at the same time, it's also representing simultaneously the geometry of a sphere.
A three-dimensional, a three ball.
Yeah, a 3 ball in this case, yeah. So it really has a solid center, if you know what I mean, because if it was my eyeball, it really would be substance and material, as opposed to the mathematical sphere, which is only 2-dimensional. But as we've already said, to be able to represent a 2-sphere, you also have to visualize it just like a 3-ball. There's no other way to show a 2-sphere visually other than as a 3-ball. So that's why that representation is also a, how should I say, a deceptive part of the way we're presented with things. Yeah,
we have to imagine it as a 3-dimensional object, but we have to understand that we're only working on the surface.
Yeah, mathematically, you only work on the surface of a 2-sphere and never the insides, whereas a 3-ball does have substance, yeah, and is taking up a real volume, yeah, of matter, yeah.
Yep.
So this is how should I say, a model of the eye, but it's also the model or the geometry of a 3-ball, and also the model of a 2-sphere. We can't separate them; they would look the same. So, if you like, this diagram is all 3 of these things. Yeah.
Yep.
So then, what I do is I stick a plane through the horizon. So this is now parallel to the ground. Yeah.
Through the center of the sphere.
Through the center of the sphere, or through the point E where the eye is.
Yep.
I'm just cutting a plane through it parallel to the ground.
Yep.
And then when I go to the next stage and tell the software here to give me the intersection curve, then it makes that green curve. And if I then switch off the plane, then you can basically see the equatorial circle of the eye sphere or the eyeball.
Yeah, which is a great circle, of course.
Which is a great circle since it's going through the center point, yeah.
Yep.
And mathematically, this is the pole. So this point 0 is the pole of this equatorial plane, yeah.
Yep.
And there's also another pole down here at O, which is also a pole of this equatorial circle, yeah. So every great circle has 2 poles. If this great circle was to be oriented differently, then the poles might be here and here, or here and here, but there will always be 2 of them.
Does that determine what's up and down to an extent?
Well, I think it does, yeah, and that's what Riemann, if you like, separated, so that you talk about the orientation on a manifold is different from, you know, the natural physics of me and you walking upright, yeah.
And if you moved that red line up so that it was going through the center, you'd also have poles on the equator.
Say again? The x-axis?
If that red line moved up to position 1, so that it was passing through the center of the sphere, you'd also have poles on that equator.
Yeah.
They could be called poles under those circumstances.
Yeah.
Am I confusing things there? I'm just basically, what I'm saying is it doesn't matter whatever, if you're giving the sphere an axis through its center.
Yep.
The points where that axis goes through the surface is a pole.
Yeah, so the pole is always, if you like, 90 degrees to the actual equatorial circle. So if the circle was a different one, let's say the circle was the one going from north to south, then yes, the x-axis would be the pole, if you like, or the points, the 2 pole points would be on the x-axis going straight through it, yeah.
I get it. I was associating the pole with the sphere when I should have been associating it with the circle.
Yeah, associate it always with a circle. So a great circle has a pole.
Right, got it.
Yeah, or 2 poles. Sorry, bipolar.
Yeah.
And what I then do in this diagram is to say, well, let's take any point on the horizon. So I've made this point here, which is for me lying on the so-called horizon circle, but because this is the horizon circle, if you like, the equatorial one. That for me is the horizon circle that's at eye level. It's parallel to the ground, and so for me it's the horizon in my eye.
Yes.
Yes.
Gotcha.
I could move this point around the circle. I've built this thing to be constrained to move around the circle. I can't move it anywhere else.
Yep.
But at the same time, what I've just done is made it. Hold on, I'm just going to undo that. I've made it. Oh, sorry. I've made it absolutely parallel to the x-axis, to the y-axis. Sorry.
Yep.
You can see that. So I've just positioned it that way to make it easier. So the basic idea being that I'm standing on the ground. My eye is at an altitude of 1 unit, and my horizon circle is now that equatorial circle of the sphere that is parallel to the ground plane XY.
Yep.
And the point here, I've made point straight down the Y direction. So if you like, that's the direction I'm looking.
So it's constrained to the circle at that point.
Yeah, I'm not allowing it to move. Yeah. Then I make a ray through E and through that horizon point, which I would then see as my direct line of sight. Yeah. If that's where I'm facing and looking, then that's my horizon. If you like, if I was looking out towards water, then that would be the top of the wall of the water that I would be seeing, would be pointing straight out in that direction. Yeah.
The line, if you were standing at the shoreline, your feet would be on the y-axis, and your eye would be where it is at E.
Yeah.
And the wall would be going up from your feet to that line.
That's right. The wall of water would be, if you like, here on the y-axis, straight up and down here. I would see nothing but blue if I was looking out to sea.
Yep.
Or out to the ocean. I mean, not to sea. You know what I mean? Yeah.
Yep.
So after that, I thought to myself, well, what are the other things that I have to? Well, what are the other planes of the eye? So if I now look at what I would call the facing plane, then what I've basically said is when I'm looking out towards something, then that would be the orientation of my face. Yeah. Yep. So I would be facing something, looking at it with the direction my nose and knees are pointing is the green line, and this plane, this reddish plane, is basically my face.
Yep. With an ear on.
Sorry.
With an ear on either side.
Yeah, exactly. And I've called that now the facing plane. So the green one I call the horizon plane. Well, the plane cutting through it is the horizon plane, and that's then the horizon circle. And this one I'm calling the facing plane, and it's going to be the facing circle. So if I go down one, then I've made where the intersection of that curve is, and when I then switch off the plane, you can see that I've got my facing circle and now my horizon circle.
Yep. And
then what I think was important was to punch in the left and what we would consider to be left and right, which is a line that I've drawn through the 2 points here where the red and the green plane meet. So the red and the green plane meet here at this point, and they meet on the other side at this point, and I've then drawn a line joining those 2 points.
Yep.
And for me, that's left and right. So if we were looking behind this guy, then his left would be over here, and his right would be on this side. Yeah.
Yeah, well, the same as ours.
Yeah. I'll just turn them to face us again.
Yep.
Or slightly. So and then the last plane that I think is important is what I call the forward plane, and the forward plane is going then out in the direction of exactly my line of sight. So it's the third perpendicular plane, if you like. It's now the one parallel to the z-axis and to the y-axis, or joining the z and the y. And if I then do the same thing in that I make the intersection point and then switch off the plane, you'll see basically these three planes now have made three different intersections or three great circles on the sphere. Yeah.
Yep.
That makes sense?
Yep.
And I've called that the forward circle because that plane, for me, is like pointing in the direction of, your nose. But it's a bit like, hold on, I'll just switch off the screen very briefly and just so it's for me, it's that way. You know, when people say, well, I'm going in that direction,
yep.
then that's the kind of movement they would normally make, you know, right? I'm going there, and
yep.
you would be kind of cutting a plane in that direction.
I was going to ask you that actually, because it wasn't intuitive. When you said forward plane, I was sort of thinking of what you've actually got as the second plane. What was the second one called?
The facing plane.
The facing plane. Yeah.
That's that one, if you know what I mean. Well, I know you know what I mean, but yeah, so that's my facing plane. Yep. I could cut a hole in here and show my face in it.
Yep.
This is the one that I think is the one that, you know, I'm cutting it that way. I'm going forward, straight direction, and the other one's my horizon plane at my eye level.
Yeah, horizon and facing are both intuitive. Forward's not. Yeah,
forward's a bit. Yeah, I know what you mean. I struggled a long time to think what's the best way to explain it, or why am I choosing something what I'm calling the forward plane. Well, maybe it'll become clearer. Hold on.
Because it goes backwards too, I think, is maybe why we sort of think.
Yeah, you're right. It could be. It's a forward-backward plane. I agree. It's going out, if you like, out the back of my head as well. If you like, it's cutting it bad.
It's probably just a brain thing, you know. Like I say, not intuitive.
Yep. Yeah. Well, definitely. Your screen share and presenting to everyone. Okay. Yeah. So I'll get rid of the plane again, so that we basically then just have these three great circles, all perpendicular to each other. Yeah. And I've got this definition of what left and right is, if you like, through this line. I'll just switch the line off as well. So the same way, I've also done a line up and down, so that you know what up and down is. Up and down would be, as far as I'm concerned, again the line that goes to the top of your head and to the bottom of your feet. I think up and down personally is absolutely clear to everybody on this planet, right? There's you know, it's nonsense to think that people don't know what up and down is.
Right, you fall down and you rise up.
Yeah, absolutely. But even without that, if you're just standing there, right? My understanding of biology is also that the circulatory system that we have in our body, the blood actually, if you like, it pumps up your right leg and then back down your left leg, right?
Yep.
And that it does that in plants as well. You know, they've got a system whereby in the morning when the sun starts to come up, then everything starts to rise up, and at nighttime everything starts to go back down again. You know, or to wilt or to wither, or and that you know that.
Go on.
No, you go.
I was just going to say there's the mechanism in our ear that balances us.
Exactly, there's that as well. Yep, there's the mechanism in our ear where it's quite clear to us. If we were to hang upside down in a tree like a bat, then you'd fucking know all about it, right? Your head would be bursting with blood towards the end of the day, right?
You mean like a so-called astronaut in a so-called ISS?
Yeah, exactly. So, you know, I mean, I think it's absolutely absurd to think that people don't have a notion of up and down. And I think that notion of up and down is clear to absolutely everybody who's ever lived. Yeah. And we know when we're upside down, and we know what up is. Up is when you get out your bed in the morning and stand up, right? And yeah, if you go to bed at night, you're going to be lying horizontal. And you definitely know the difference between those two things, right?
Yep.
So So for me, it's perfectly clear that that's up and down, the top of my head, or what's straight above my head, the so-called zenith, yeah, and where my feet are then. And the other one that I think is important is obviously the forward line, which is similar to the line of sight in that it's kind of going through the back of my head or the back of my retina, out through the front of my eye or out through my nose, pointing in the direction of my knees again, yeah?
Yeah.
Or parallel to the...
So the forward plane sort of slices through, vertically slices through the horizontal.
Yep. Horizontal circle. Yep.
Through the line of sight.
Yep.
And all right, through the horizontal plane at the line of sight.
Yep. So there's that forward plane, and you can see the line of sight's lying on it. Huh? Let me just get rid of the forward backward line so that you can see, and that green line of sight is also directly on the plane. Yeah.
Yep.
Okay.
Can this representation be done in perspective mode as well as orthogonal, or is it just always orthogonal?
No, I can actually choose here between different modes. So that's the perspective mode. You can even set up GeoGebra so that if you've got these Cinema 3D glasses, you can wear a pair of glasses.
Right.
And you could see it then slightly more three-dimensional. Or you can even do an oblique projection, which makes the thing look, oblique.
Yep.
So I prefer to just stick on the normal 3D version here, or the orthogonal projection, rather than the perspective one. The perspective one sometimes help for a slightly better visualization. If I just switch between the two, you'll see slight differences, but they're not many. And to be honest, I've never tried wearing these glasses. I'll actually need to do that. I know the kids have got some lying around, just to see exactly how good it actually does it.
Yeah.
But yeah, I'm staying on the orthogonal projection.
Yep, no worries.
So after that's kind of been set up, and it basically it's all done by planes cutting through a sphere, right? That's how these circles got made. So that's all geometrically easily, how should I say, determined and easily seen by anybody. It's the same, Euclidean spherical geometry that's been around for thousands of years. So nothing new there, except that I've tried to define what I think are the three main planes, and I've called them horizon, facing, and forward. Yeah.
And those planes all create great circles on that sphere.
Yeah, they have to, because they're going through the center of the eye. Yeah. So I put a couple of points there. This plane, horizon. So this is when I then set up some of the rectangular figures around it. So we can actually ignore this because it's the same as the plane that went through the horizon, but it's where I now start to set up some points. Let me just put a three. So I've got a horizon wall, a middle wall, a right wall, just where I start to set up this kind of rectangular frame that goes around it. If I put this one on, I've got the roof, I've got the left wall. So and basically, I'm just putting a kind of rectangular frame around the sphere of the eye so that I can set up this line up here as well.
That's the one that you
that I can attach objects to. Yeah.
Yep.
So
when I was having a play with it, I went through each of the objects and I looked at that line, and I was trying to figure out how you actually constrained the movement of the objects on the plane to that line.
That's done with this here. You say a point on object.
So
you can, I can kind of select a point, or I can make a point, and then I can join it to the object by attaching or detaching a point. So I can either choose a point on an object or make a point and then attach it to another object. So that's one of the tools that GeoGebra brings.
I probably shouldn't ask these questions about the actual construction.
No, that's okay. Well, yeah, I know what you mean. If other people are watching this, it might not interest them so much. But just let me get rid of that then. So from those two planes, I take the intersection of two planes, and that's how I get this blue line formed.
Yep.
This line that goes, if you like, on the it's the intersection of the roof and the right wall.
Yep.
And it's basically just over that line that I attach points, and then I can move it outwards. And because I've set up all these planes, they don't look as if they go on forever, but they actually do, obviously. Yeah.
And the lines go on forever as well.
Yeah.
Yep.
Which means that, you know, having this 3D construction means that I can go away out here and draw an object within this rectangular frame, and then show how the rays of light of that object are hitting the eye. So that's why I kind of set it up that way. But I usually just hide everything apart from this one line where I move the anchor point of whatever object I've drawn up and down, or further away from the eye and closer to it.
Yep.
So I'm just stepping through some of the construction points here. I've done the same with all those different. So each of these planes, if I was to put them all back on, then they've all got these intersection lines. So there's the intersection line of those two planes here on the top right, or the one here on the top left, or the one at the bottom. That's the intersection with the ground plane, which I've hidden at the moment. Yeah.
Yep.
So that's how, basically, so that I make the planes first, and then I take the intersection of those lines, and I know then that I have a rectangular frame, if you like, that's extending as far out as I want and as far behind as I want, on which I can attach objects.
Yep.
So let's just switch all that back off again, because it's so that should be us back to where, to the naked diagram. Yeah, so that's the basic setup of all those drawings where I'm trying to show what's happening on the eye, or on the retina, or on the geometry of vision. It's always basically the same setup. I start with a sphere, that's my basic setup, and then I draw the rectangular construction around it so that I can move objects.
Yep.
So the point I usually use is a point A, which is on this right roof. And that's the point I can then, I've again attached it so that I can just move it up and down. And then I can attach other things to it. I've also drawn the line, if you like, that is perpendicular to that one.
Yep.
So that I can attach things hanging on to that as well.
So they sort of, if you do another line vertically perpendicular on that line and attach it to that line, it will move constrained to A. That's
right. So the whole thing's constrained.
Yep.
So I've drawn 2 points on that line.
Yep.
Or they're themselves the intersection points of those lines now with this one. If I was to switch all that stuff back on again here, the wall and the ground left, the roof left. Yeah, it's the roof left, sorry. Then that point there is again the intersection of this line with this perpendicular line that I drew from A.
Do they just automatically get put there, those lines?
They were the ones that I made from the intersections of these planes again.
Yeah, but you made the lines, but did you make the points, or did the...
Yeah, no, I made the points. I just said, well, show me the intersection point of that blue line and this new black line that I've drawn perpendicular to the other one. Yeah.
Right. I'm sort of turning this into a bit of a lesson for me.
Yep, no, that's okay. Yeah, I'd like other people to be able to start with the same construction and make further observations. Yeah. Yep. So I do think it's important that. And GeoGebra, as I say, it's not difficult, but it's good to have a starting point rather than to start with a scratch pad, if you know what I mean.
Well, actually, the last few minutes we've been talking about it is like I played with it yesterday, having no idea what I was actually looking at. And now you've answered most of the questions I had.
Okay, good. Just get rid of the wall and the roof again. Yeah, so I've made basic some of, as I say, some of these lines, and I'm leaving some of them in so that you can see what's happened. Why did I get rid of that ground? Sorry, roof left.
The other, you have the one that goes through A, and
where did that one go?
The other roof one.
Yeah, I'm missing that roof right. Sorry, that's the one I needed. Yeah. Yeah, so the one that A plays on. And if I just keep going down, I'm just going to point D. I'm just stepping through the construction protocol here. Then you can see how I've basically just built up the rectilinear frame, right?
Yep. So the construction protocol basically just makes a list of each of the things that you create.
That's right. Yep. And then afterwards, the construction protocol, you can move the construction order about. So you can move things to the beginning of the construction or back, but you need to watch that if there's dependencies, like some point needs to be there before you can draw a line, then you obviously you can break it as well. So,
yep.
But the construction protocol basically just lists every single object that you've drawn. Yep. And then
why would you want to do that? Why would you want to actually change the order?
Well, sometimes when you're starting out with a drawing, you sometimes do things in the wrong order. So, you know, for example, I think I made the horizon plane and the facing plane, and then I started on this Euclidean construction, and then I drew the forward plane in afterwards. But on retrospect, it made more sense that I bundled them all together because they weren't dependent on the rest of the construction, and it's easier then if I'm stepping through it to show, if you like, everything grouped together, you know, when they make sense together.
Yep.
But yeah, sure. If you think about it in advance, you know, then you don't have to change your construction protocol. But sometimes while you're doing it, you think to yourself, okay, so let me get rid of all these parallel lines so that basically all we've got left is the actual roof line, the point. I'll hide these points as well because I think they're kind of useless to show.
You don't really need that right roof line either, do you?
No, don't need the right roof line either. No, sorry, the left one. Yep, that one. Yep. Good. I've still got some points hanging about here, but we can get rid of them in a minute. So the next thing that was important was then to think, well, okay, this point, which is part of this Euclidean construction, if a ray of light was coming from that one point and it was going to the center of the eye, because that's what would happen if I looked at it, yeah? If I looked at that point, then it would go through the center of the eye, then and onto the retina, that's right. And if I was then to move this point up and down, what would I actually trace on the sphere was the question that I asked myself. What would it look like on the retina? And when I say I'm moving this up and down, this is the same as what we discussed with the water. I've constructed this to move up and down, but if I was to trace what was happening in real life, there will be points, or light will be coming from all points on this frame and not just from the one, and they would all be coming simultaneously to the eye. Yeah. Yep.
Actually, just looking at that then was making me think of something a little bit different about the sun setting.
Okay.
You know, the point A is the sun moving away across the flat plane in front of you, and the point is actually moving down from the pole to the equator on the sphere.
Yep. Yeah, absolutely. It's exactly what's happening. If this thing was just moving away from us, rather than it would also do exactly that, sink in your visual field of view. Yeah.
Which is why people think the sun goes down.
Yep. Absolutely. It's got nothing to do with that. So let me just go through a couple more of the points. I've got some segments here. Hold on. Just want to see what these segments are. Oh, yeah. Those are the segments of my equilateral frame. So, again, you can see that when I move this back and forward, then the frame is moving back and forward. Yeah.
Okay. Is that made up from those lines that you had in earlier?
Yep. Yep. But I'll just switch them off because the important point is actually this intersection point that I've now made on the sphere. If I zoom in a little bit, then you can see I've made a little red dot, which is literally just the intersection point of that ray of light with the sphere.
Ah, and you can actually tell GeoGebra to do that. Well, obviously.
Yeah, I can. I can tell them to make that intersection point for me. Again, that would be done over the intersect, this one.
I can't see your mouse.
Oh, is it so? You can now, right?
Yep.
No, but you can't see the. Oh, you can see the top thing. Hold on. If you look right.
Yeah, I can see it.
You can, yeah. And can you see it's? Sorry, it's now saying intersect here.
Can't see it saying intersect anywhere. No.
Ah, okay. Because my mouse is actually in the green part of the screen, so above where the. Hold on.
I haven't got a green part of the screen.
Hold on. I'm just going to press stop here. Stop screen sharing or stop presenting. All right, it's doing the whole thing. Yeah. Can you see? Can see where my mouse is? Can you see the line above my mouse so you can see these little figures? No.
I can't actually see your mouse at the moment. Put your mouse over.
Hold on. I know what I need to do. Hold on. I'll just present the whole. Just present my entire screen. So. Present to everyone. Now you should be able to see that top line, right? If I go up to here to see these points, can you see that now?
Yeah, I know. I can see them all before.
Yeah, and then there's this intersect. That's the command that you would use to understand the intersect for this point here, this red point.
Yeah. No, I could see the menu bar before, but I couldn't see the drop down.
Ah, okay. Yeah, the drop down wasn't showing for whatever reason. Yeah.
Yeah.
Okay, so, and then I decided to put the trace of that on. So as I now, the trace of that point. So as I now move this frame back and forth, or this point back and forth, then the ray of light coming from that point A, either as I move it, it would trace out that line, or if this whole thing is static and each one of those points is emitting light, then that's also the image I would see. If, you know, because that's clear to you, right? And hopefully clear to everybody else. And I know it's clear to you, but this idea of me making this frame so that I can move it is just the same as me not moving it and saying that there's light coming from all the points on this line, yeah? Hitting the eye.
If that was a solid line and you were looking at that solid line, that's the impression it would make on your retina.
That's right, yeah.
And you're showing that by representation on a larger sphere.
Yep. And also this construction thing, you know, that nothing's really moving. I'm moving this to demonstrate stuff, but if this was just a real life situation and light was coming from different points on this blue line, yeah, then the light hitting the eye would also make the exact same shape here on my retina as it does by me moving one point. So whether I'm moving one point or whether everything's static and there's lots of points will give you the same image.
Yep.
Okay. So I don't want people to be confused by me moving that point up and down. You know, they also need to understand that that doesn't really matter, you know, if you know what I mean. It's still the same image on your retina.
That's one of the problems I was having with that side-on diagram with the wall of water discussion we were having. I kept thinking about the wall of water being created as you moved, but that's not true. It's there all the time.
Yeah.
It's only the boat that moves on the water.
Absolutely, and sometimes maybe this diagram would have been confusing because of the fact that I've set it up to move so that I can demonstrate specific things, but the real life would be light coming from all these points all the time and not just when I move it.
I think that happens, you're probably going to show that later, but when you've got a rectangle or something, you can see that the rectangle gets smaller or larger, but you can also see that if it's still there.
Yeah, exactly.
The representation on the sphere is still there.
So I think this is a very important point, that when I move, I can make this a bit bigger or whatever, or smaller. When I move this line out, then you can see it going towards the eye line again. Yeah, this
To the horizon.
This trace going towards the horizon, yeah, and towards my line of sight. Now, what's also, or what was for me very eye-opening, was the fact that, let me just zoom in again, was the fact that the trace here on my eye looks very much like a circle, right? Or a part of a circle, or an arc segment of a circle.
Yep.
Yeah? And that is in fact the case, that this red line, if I continued it, would go through here, would go through that point, would go down here and round the other side. So that, guess what? It's a great circle.
Yeah, well, it has to be, doesn't it? It's been coming from the center.
Yep, exactly. And I just thought this visualization was then good. So if I go a little bit further now in my construction protocol, that's me drawing the whole of that quadrilateral again. There's the other one. There's a bottom one too, and I start to draw different rays. So if I now start to draw the rays from this point to the eye, from this point, and from this point to the eye, and there should be one more.
How do you actually draw those? Do you actually draw them physically by clicking on the point and then on the corner?
Yep. So let me just zoom out. I said zoom out, please. So, yeah, so it's just a question of taking one of those rays here. You can take a ray, and then you just choose your starting point and your end point, and then it will draw the ray. So you're always best going from the eye out to the object, so that the rest of the ray is here. Going up that way rather than the other way, because if you did it from the point to the eye, you'd have a whole lot of lines coming out the back of your eye.
Gotcha.
So, but since it doesn't matter, you know, since straight lines are reversible, i.e. they have a backwards and a forward, it doesn't really matter for the geometric construction, right?
That might be another way. I mean, in a different diagram, that might be a way of actually showing it on the retina.
Yep. Yeah, if people needed to be convinced that it all happens at the back here, then that would be one way of showing it, But I think anybody, well, I hope people can see that it doesn't matter whether it's on the front or whether it's on the back, apart from the fact that one of them's flipped on its head and left to right, It's immaterial from a geometrical standpoint.
I think most people understand that you know, the image is reversed. Yeah.
So I've drawn, if you like, all these different rays, and I think it's poly 4 and 5. Yeah, so if I now look at this whole diagram, then I think you can see what's happened from every single point of those rectangles here. From the bottom, from the middle, from the sides, I've drawn those rays straight to the eye. And if I switch off all these quadrilaterals again so that it's not visible, then you can basically see now just the rays. It's a bit messy, the diagram then, but if I move this back and forth, then you can see how all the rays change depending on the distance of those quadrilaterals from my eye.
So, and they are all drawing out arc segments of great circles.
And exactly, that's the interesting point, is that each single one of them, if I show now these individual red points where they're meeting the sphere, which I hope you can see.
Yeah, I can see them.
You should be able to see them coming up. And let me get rid of the rays now, because they're probably more distracting than anything else.
Yeah, I'm already imagining that those points are representations on the sphere of the corners of each of those rectangles.
That's exactly what they are, yep. And if I now move this back and forth, then you can see how these points all move away.
Yep.
And you can see how all these points come back. Yep.
Yep.
And each one of those points is tracing out a great circle.
Yep.
A different one. So the ones along the horizon are already tracing out the horizon circle, which we've already got. But the ones here at the bottom and the 3 ones at the top, I've got 2 traces on at the moment. You can see that, you know, they're tracing out great circles.
Yep.
So that's the important part, that when we're viewing or when a ray of light is hitting your eye, and either I'm moving that ray of light or the movement is only representing the fact that there's lots of rays of light from each of these static points, either way, I'm getting a great circle traced out on my sphere here.
Yeah.
Which is causing a visible to be impressed upon my retina.
Yep. The visible as a representation of the tangible.
Yep. What we see, basically. Yep. The visible objects as opposed to the
things that the mathematicians have never spoken of. That's right. Language.
Exactly. The things that for 2,000 years nobody's discussed. Yeah.
Yep.
Which is a huge red flag.
And another interesting point from my point of view is we're probably the only 2 people on Earth discussing at the moment.
Absolutely. Yep. That's what makes it even more terrifying, if you know what I mean. Why is it just me and you, Glenn? Something's going on. Yeah. Why the fuck did we get chosen? Yeah. Anyway. So what I did then was to actually create this circle here. So this blue circle that I've created is let me just get it here in front of me. It's the intersection. It's the intersection curve of the plane of the roof right edge, which I'm just going to put back in now.
Yep.
So you can see it. Plane E roof right edge is plane E roof right edge is this one. So if I bring this round the other way, then it's a plane, right, that's going through the point RT0. Hold on. No, I'm confused with labels. It's going through the eye. It's going through the point A, and it's going through the bottom of my rectangular frame, right? That's what I've set this plane up to be.
Through the bottom of the rectangular frame.
Let me put the the right wall back on. Nope, sorry, the left wall. Yeah.
And then the plane down the bottom.
Nope, sorry, it's my rectangular frame.
You want the floor one, don't you? Or
yeah, I want the floor one. Hold on, sorry, I'm just looking to find it. Is it ground left? Yeah. Oops. No. Sorry, I should have prepared this bit better. So it's the plane of the roof right edge. I've got the plane of the roof right edge is on, and the plane of the is RT0. Hold on, I'm going to switch on this point right enough just so that I can remember what the fuck it was. Sorry, just one sec. RT0. RT0 is the right top 0. Yeah, so that's that plane. It would be the same as the, let me switch that line on again. The sorry man. This here. So it's basically the plane that goes through that line.
Yep.
That's, yeah, at the top here. So it joins this line with the center of the eye, and then it cuts through down to the bottom.
Is it going through that bottom line? That bottom?
No, it's not.
Uh-huh.
You can see it's not if I look on it as a side view. Yeah, approximately like that. Yeah. So all I need is for that plane to join this line in the center of the eye, because that's all you really need. You only need 3 points to define a plane. So I'm taking this line, those 2 points, A, and this point on the line, another point on the line, and I'm using the point E, and with that I'm defining a plane, and that plane then cuts through the sphere and cuts through the bottom, but doesn't reach the right-hand side of my rectangular frame. Yeah.
Oh, I see. The rectangular frame, the floor of it's based on the bottom of the sphere.
Yeah, the floor of it's the bottom of the sphere, and this is the left-hand side, equidistant from this line. So these two, yeah.
Yep.
If you want, I can put them back on again to make it clearer.
No. I was just sort of
maybe just these four, so that you can, so that these 4 lines would be the ones that are defining my rectangular frame. These 4 blue lines.
Yep.
And basically,
what I'm having trouble with is the line, the roof line that A is on.
Yep.
That's at what? Is that at 3?
Yeah, that's at a height of 3. Yeah.
That's
It stays at a height of 3. I've made it to be 3, the height of the roof.
Yeah, so the other one would have to be for the roof, for the floor, for the plane to be going through the floor line as well. That you'd have to, because it's at 0, isn't it?
Yeah.
That's what's confusing me. That was, yeah, now I get it.
Yeah. You good?
Yep.
So, and I've done the same then for the other planes. If I go here to the hold on, I maybe need to put them back in. So that side, so that would be the other plane coming from the other side, and the one from the ground edge and the one from the ground left edge. Now that's already looking a bit messy, but I've basically just done the same thing that I showed with the one with this blue plane. I've done from the right hand top of the roof, from the other, and from the left and the bottom as well, so that I'm now getting 4 great circles which correspond to these 4 red points that I had.
Oh, now I see what you're doing. Yep.
Yeah. So that was the one red point. If I move A, you'll see that the one red point traces out on the top great circle.
Yep.
Sorry, you can ignore this middle one, but that's the point that gets traced out from the top left-hand corner of my rectangular frame. That's the point here that gets traced out by the top left-hand corner of my rectangular frame.
Yep.
And those 2 ones down here are the ones that get traced out by the bottom left and the bottom right of my rectangular frame.
Yep.
Maybe it does make sense to put these quadrilaterals back in, so that, you know what I mean? That's those were the points, and those were the rays coming from those points.
It's probably making it too cluttered with those in.
Yeah.
But yeah, because the way you explained it just then made perfect sense to me, because I could see I'm basically looking at those little red dots as the corners of those angles anyway. So
that's right. And I'll get rid of these middle points here at the moment. They're the ones that are, if you like, in the middle of the eye, the rectangular frame. I can maybe
on the equator, on the horizon line.
Yeah, I can maybe take that object away, and this little one is away as well. Yeah, so that you really only have the 4. And just let me get rid of that plane now, so that doesn't get in the way. So we've got the 4 rectangular edge lines from our rectangular frame. we're drawing out how these things work on the retina, and you can see that each of them is drawing a different great circle on your eye.
Yep. Or a different arc segment.
Well, an arc segment of a great circle, yeah. But if you can see that what it's basically doing is following exactly that plane. So it's actually on where that plane cuts the sphere.
Yeah.
And that's the tie-in, if you like, to normal spherical geometry. That ray of light is tracing out what the plane it's sitting on is making happen, if you know what I mean. Because we're on this plane because this line has been drawn, and I can move this point along this line. And that ray that's been traced out on there is exactly the plane. Is exactly on the great circle that plane is cutting through the eye with.
Yeah.
So that's where you can start to see the connection between planar geometry and spherical geometry.
Oh, I get you. I was wondering what you were getting at there with that. Why you were sort of thinking, yeah, well, that means that line is going to travel along that plane. That all the rays coming from that roof line are going to travel along that plane, and
they're going to make a great circle.
Yeah.
Which is exactly the kind of, the geometric demonstration that Thomas Reid was trying to get at. He was basically saying, guys, light traveling in straight lines on planes leaves spherical great circles on your eye.
Yeah.
As part of the visual impression. So we now have, if you like, these one great circle here, or the red point is making an arc segment of that great circle, but basically it would be a whole great circle here as well. Yep. And the bottom points are making these yellowish ones, yeah. And you will note that they're all different great circles.
Yep. One thing too that I thought of just then was that these arc segments of great circles that are on the sphere of our eye is not actually what our mind is seeing, though.
Nope, I agree.
Our mind is seeing those straight lines.
Yep, our mind is seeing the normal Euclidean straight lines of the top wall here, right? Or of the quadrilateral that's facing us, or whatever object it is we're looking at. Because if we're at the center of a sphere, then you don't see that outward curviness. You get back to the same thing. That's why we see Euclidean and we don't realize we have spherical vision.
Exactly. That's where it becomes tricky. It's sort of like there's a magic conversion that happens between the surface of the sphere and the center, where it turns back from spherical geometry to Euclidean geometry.
Yep. And the very fact that we, the projection that we have is a projection from the middle of the sphere looking outwards. That's our natural perspective vision. And a projection that you would make for a map, for example, would take the center point out of here and put the center point, for example, in the North Pole, and then make a projection onto a flat planar surface. But what we have to realize is that our eye works basically also as a projection onto a spherical surface, but we are at the center of that spherical surface. Yep. And that's why we see things straight, even though we don't have planar vision or Euclidean vision.
Yep. Yeah, like I say, that magic conversion that occurs.
There's a sneaky kind of invisible part in there which we don't realize because of the way we're hardwired. Yeah. And the fact that you can't see the curve of your own retina. Because if you're like inside your head looking out through your eye, then you can't see the curve of your own retina. In the front or the back.
We can't attend to it, as Mr. Reid would say. Dr. Reid would.
Exactly. You can see it if you're really close up to things, or the other way when you're looking at the spherical sky above you, or the what appears to be spherical, and that's as you say, or as he said, we don't attend to it, so we've missed it all these thousands of years.
Yep.
So for me, the main point is that if I was to hold on, let me just take this construction to the end. So I've got some, again, all these planes are cutting those different circles, right? I know it looks messy here, right? But what I'm basically showing is that using planes cutting through the sphere is basically me making those great circles that are on the eye. Yeah?
Yeah.
And that's actually what's, the 4 points is and now you can see these planes, if you like, changing, right?
Yep.
The further out I go, you can see that that yellow plane, for example, at the bottom is noticeably shifting up and down. Yeah.
Yep. Maybe that's part of the magic.
Yeah. It is. Yeah.
Yeah.
So you can see these planes rising and sinking, if you like, and when it's really close to your face, then you get these kind of funny flip over. But yeah, but before I don't want to get lost in too much, let me just take the construction here a little bit further. So that's when I just start to make segments joining the points on the arc. So I've basically just made a segment there so that we can see better what the actual image of the square is on my retina.
Yep.
And I continued to do that until I have the full square basically in front of me. And then, then I can switch everything else off basically. Yeah, I'm just about to do that. I think all these, they're just confusing then, aren't they?
And just keep the rectangular lines.
Yeah. So I'm just keeping my original 3 facing forward and horizon circle. Yep. And then showing, if you like, just these 4. Oh, did I switch one?
Arc traces there?
Yeah, I put these, I should have put these ones on. Arc left, arc right, arc roof, and arc vertical. Yeah. So that's.
I can still see the traces of the curve.
Yep. So I've just left that one trace on, but that's
it doesn't matter.
Yeah, that's the rectangular frame that's in front of my eyes that I'm moving with the A. Yep. That's the shape it's leaving, and all those lines are arc segments of great circles.
Yep.
So because all of these points each individual point on this line would also be part of some great circle. Yeah.
Yep.
So the whole thing is made up of great circles, or arc segments of great circles. Is on a sphere. You can draw any multi-segmented, straight-lined, rectangular figure, or any figure for that matter. N segmented. Yeah.
Yep.
And
circles
that
are a different case.
Sorry, say again.
Circles are a different case.
Yeah, circles are a different case. And if I then
circles.
Yeah, if you're viewing a circle, absolutely. Yeah. So we're staying here. Now you can see that how that great circle, the brown one that I've drawn there, is moving, and depending on whether this is moving. And that's the thing I want to make people understand, that when we go to the two-dimensional representation, then hopefully they can see that it's perfectly correct to show that your eye sees in great circle measures, because every single point that I'm seeing here is part of some arc segment of some great circle, so that when I go to that two-dimensional view, it doesn't matter in which orientation this sphere is, right? If I take a cross-section through the eye in any plane at all, then I can always show what's hitting the eye in terms of a great circle on the eye.
Is that only with rectilinear objects?
No, as you say, there is the difference between the circles and how you see a circle, and we need to handle that separately. So at the moment, yes, I would say for this diagram, it is to do with rectilinear figure. And we need to look closer at what it means for circles. I've actually started another one on that, but it's not finished yet.
Yep.
So you are right, they are different.
And I was sort of thinking about a squiggly line.
Yeah. How does a squiggly line look? Yep.
Yeah.
But I need to do both. I need to do that one as well. Absolutely. But the main thing I think that what I want people to take away is just the very fact that since they're all transcribing here on my retina or on my eye arc segments of great circles, and this is me showing the model of the eye and rays of light hitting the eye, then it's perfectly okay for me when I take a two-dimensional cross-sectional view of this in any orientation whatsoever. It doesn't matter where my plane's cutting through. Then the representation that we show when we're looking at a two-dimensional object, I'll just open one now so that people can see our normal, hold on, make a new window and open the, then from a two-dimensional perspective, it's that arc segment that we're looking at, right?
Yeah.
So whether, coming from the three-dimensional model, let's say, where did it go? That's behind it.
Yeah. That's an arc segment of one of those lines.
Of just one of those lines, whatever plane that we've taken to cut through the eye, whether it's from the top, whether it's in the middle, whether it's sideways, either way, I'm going to get that that two-dimensional arc that I can then look at from a cross-sectional point of view to show what's happening.
Yep.
So that was the intention of that. I just wanted to make sure that people understood, that it wasn't just pulled out my arse, but looking at the eyeball as a real physical object, understanding how rays of light hit it, and understanding how these arc segments of great circles work, allow me then to make a two-dimensional cross-sectional view that is a correct description of reality.
Yep, because you're showing where the rays of light impact on the eye, surface of the eye, or on the retina, in that one particular great circle.
That's right.
Or that one particular arc segment.
Yep. So I'm looking at it from a specific angle. It could be oblique. It could be. It doesn't really matter because every plane going through the center is a great circle. So that means that any cross-sectional view I take at all, I can represent it like this and analyze what's going on.
Yeah.
Now, when you actually hit the surface of the three ball, then it'll actually be more of a, how we're always talking here in this two-dimensional diagram about the distinction between 2 points, and that when these 2 points become so close that they merge into one light source, then you can't see anything. Now, on the retina, it's actually a surface, right? If I'm thinking about the rods and cones, which they say are in my eye, then because I'm only looking at one great circle here, I need to look at the lateral great circle as well, that like the other way around. So not just this view, but the sideways view, like turning it.
Sort of like a spotlight shining onto the surface.
Yeah, exactly. So in reality, it would be more of a surface like this whole red surface. That's in reality happening, but because I've taken a cross section and I'm just looking at 1 point, then we're only showing it here in this two-dimensional view, and we're talking about the arc segment length between 2 points. But normally it would be the whole surface of light that's being illuminated onto the retina, and that would be a surface or a part of the surface of a sphere.
Yep.
And the good thing is that the arc segment lengths and the angles here are all proportional to that surface area. That's one of the things about spherical geometry, and that these proportions are the same. So the proportion of this arc segment to the next arc segment is exactly the same proportion as if I shined a spotlight onto my retina. I'd have a bigger circle and a smaller circle, and the surface area of the bigger circle and the smaller circle are in the same proportion as this arc length to this arc length.
Actually, you show that with a diagram, I think, in one of the natural perspective videos.
That's right, yeah. I just wanted to make it clear for the people that when we come to using these geometric diagrams, that's the source of why we're allowed to use these diagrams. Not that somebody comes and says, hey, wait a minute, there's too many assumptions in this diagram. Why are you assuming this, that, and the next thing? And that's why I thought it was good to maybe just come from this demonstration here of how it works, why we're allowed to use arc segments the way we are.
Yep. The one question I've got at the moment is, this is all presupposing what? That each of these things is happening in milliseconds.
Yep.
Because the eye would actually be, like we've got the one green line there showing the line of sight.
Yep.
This is all based on the line of sight remaining in that position. But in actual fact, the eyeball would be flicking around.
Yep. It would be flickering around. But I mean, the good thing, the very fact that a sphere is spherical, it doesn't really matter because it's equally uniform in all directions. If this was pointing to somewhere else, then the geometry would still be the same. We'd have the same, you know, everything would be the same because a sphere is uniform in all directions.
Yeah, I was just had me sort of. I'm still a little bit not convinced. No, that's not what I'm saying. That the image that we're seeing there at the moment is the image that would be on the eye with the eye line, with the line of sight being exactly where it is at the moment.
Yeah, because if we were just kind of looking straight, then that's the whole image. We'd see a bit of the top corner, but we'd be concentrating on the middle of the room, if you know what I mean, or the middle of the corridor, wouldn't we?
Yeah. What would happen if you shift that middle line, that line of sight, though?
Well, you know, I don't think it matters at all because if I was to move this whole thing, you know, up so that this line, then because a sphere is uniform in all directions, it's still going to be the same geometrical view, right? Yep. This thing is always still going to be a tangent to the sphere at any orientation.
Yeah, we're not looking at a different part of it. We're still looking at that whole same object.
I mean, at the moment, I'm saying my eyes are pointing straight to this middle point here.
Yeah.
But if I was to move my eye to look directly at this point, then obviously the shape would change on my eye, because what's the best way to describe this? The same way that sometimes when I look at something, it doesn't look rectangular; it looks like a trapeze or a parallelogram.
Yeah, yep. Like we're talking about with when you're looking down along a fence line.
Yep. Yeah. Exactly. Yeah.
You just take the image of that and make it a two-dimensional image. It's just a quadrilateral.
That's right.
A quadrilateral with the side nearest you being longer than the side furthest away from you.
Yeah, which is this foreshortening thing. Yeah.
And but it actually looks like just an oblong on a flat plane.
Yep.
Yeah, I get you.
But from a geometrical point of view, it doesn't really matter because the sphere can be turned in any direction. Those lines are always tangent to the eyeball, right? Because the eye sphere, then this ray of light is hitting the ball at a tangent, right?
Yep.
And that's the same for every single ray of light hitting the eyeball, because the eyeball's a sphere. It's always going to hit perpendicular on a tangent. The same way they tell us, you know,
at a tangent. Hang on. How?
Well, if I go around to the other side, then this this line, this ray of light coming from this point and hitting the eye here, it's absolutely perpendicular to the surface of the sphere at that point, right?
Oh, and then the line that's being created. No.
Well, directly at that point, if I was to zoom at that point, then there would be a tangent line on the surface of the sphere. But obviously, a surface is always curved, the sphere, so you would have to make an approximation, if you like, of the lines there. Let me just zoom in. So there's the ray of light hitting the eye at that point.
Yeah.
Now, that point,
absolutely perpendicular to the surface.
Yeah, that's absolutely perpendicular to the surface. And if I was to draw a tangent line here across here and one up and down, then at least locally they would be absolutely straight lines, right? That's what they tried to sell us, that locally on the surface of the Earth, for example, it would be flat, right?
That's where their level comes from.
Yeah, exactly.
Hey, that's a good point, actually.
Yeah, so I think that was about all I really wanted to say. I just wanted to make sure that the people understood that we were going from a three ball, from a model of the eye and a geometric demonstration of the spherical geometry to our two-dimensional geometry is perfectly legitimate, because everything's happening on great circles or arc segments of great circles. Yeah, and I just want people to have in mind that, you know, when we say these 2 points and the arc length, and, you know, in reality, we're really talking about the surface, as you say, the spotlight of a torch shining on the retina at the back here. But it's the same on the front as well, because a sphere is uniform and constant. Yeah, just so that there's no, the people understand how we made those inferences to use these kind of diagrams.
Sorry about going off on the tangent there.
No, not at all. Not at all. No, it's something we could actually dive into. But that's I think where the mathematics is involved. They talk about parallel transport, which is a mathematical construction of moving planes around a sphere, and basically those tangent planes at any one time. So if I was to draw a tangent plane to this point, then that's the way they mathematically describe things.
Is that part of their so-called geodesy?
Yep, that's geodesic maths as well. Yep, absolutely, same thing.
That actually, yeah. At some point, I reckon that'd be an interesting discussion to discuss that, to go off on that tangent and discuss how they created their level, their bullshit level.
Yep, absolutely. So say it might be a wee bit too, I don't know, too much maths at the moment. That's why I'm stayed away from it at the moment. But
I realise now that the main purpose of this hangout was to make it, well, to show people that you're not basing that side-on diagram on any weird assumptions. You're basing it on this spherical geometry.
Exactly.
Showing that there is a definite relationship between the three-ball tangible and the two-sphere.
Yep.
The two-sphere visible.
Yep. Yeah, so I think that's, if you want, we can sort of cut it off there, because I just wanted to make that. And, you know, I think when we then concentrate on showing how things work in 2D, not only is the diagram simpler, and I think easier to explain to the people, they just need to get into their head this way of looking at things. I mean, I know you had your trouble as well at the beginning, trying to, you know, or wanting to understand, well, how does it actually fit to what we see? And this isn't a diagram that's showing what we see. It's a diagram explaining how light hits the retina and how the geometry is arc segments of great circles of the real natural physical eyeball that we all have, and the way light behaves. So it was just to tie in that connection better. Compass. I'll just stop it there for the moment.